I welcome you all for this presentation. In this presentation, we are going to discuss about one of the famous algorithm, that is data encryption standard. In short form, we can call this algorithm as DES. This is the overview of this presentation, introduction to DES. Then we are going to look into both the encryption and decryption using this DES algorithm. Under encryption, we are going to look about the initial permutation, then DES round structure, then DES expansion permutation, then substitution boxes, then permutation box, then DES key schedule, followed by summary of this presentation. So the decryption part is similar to the encryption only, but the reverse operation we have to perform. That is the only difference. Other than that, all these steps are similar to that of encryption. So before going into the encryption and decryption process, we have to know the history of this data encryption standard. We already know what is a block cipher. This data encryption standard is also a block cipher. That means here we are considering blocks of plain text and we are applying the encryption algorithm over it. So blocks in the sense 64 bits or 128 bits likewise. Here this data encryption standard uses 64 bits of plain text to the algorithm. So it is widely used block cipher in the world and it was adopted in 1977 by NBS. Now it is the NIST. That is for the standards organization. As FIPS publication 46, this data encryption standard was published, and this algorithm entered 64-bit data using 56-bit key. This numerical you have to remember always because it is a standard. That is 64-bit data using 56-bit key. And it has widespread usage, but now it is deprecated because of the key size. Because the key size is only 56-bit. What notion we have is, if the size of the key is large enough, then we mean that there is more security. So there are many controversies exist for the size of the key. Later on we see. So this is deprecated, but this algorithm acts as a base for many of the variants of data encryption standard, like double dash, triple dash, all those things are there. In order to have more security, we are having different variants of this DES, but the foundation of all those things are this basic algorithm only. So we have to understand this DES in a better way. Coming to the history of DES, this IBM developed a Lucifer cipher. So before this DES, the work or foundation work for the DES was the Lucifer cipher only. This Lucifer cipher was invented by the team led by Feastel. So only here the Feastel cipher structure is used. And here it uses 64-bit data blocks with 128-bit key. In Lucifer cipher, 64-bit data blocks with 128-bit key. But for DES, it is 164-bit data blocks only, but 56-bit key. Half of the size is reduced. Then they redeveloped as a commercial cipher with input from the NSA, that is NIST and others. And in 1973, the NBS issued a request for proposals for a national cyber standard. So at that time, the Feastel team submitted this proposal. They revised the Lucifer cipher and submitted this proposal as a DES, and it was accepted as DES. But there are, at that time itself, there are many controversies based on the size of the key. But they proved that with this key size and with these much rounds, they are getting a better security. So with that proof, everyone accepted that. But still some controversies are there, and this cipher is deprecated. But this acts as a base. So only we are learning. So the DES design controversies, or although DES standard is public, was considerable controversy over design. That is the choice of 56-bit key. That is the earlier version of DES was the Lucifer cipher. That is the base for DES. There they used 128-bit. But why they have reduced the size of the key? Because we know the notion that if you increase the size of the key, then security is good enough. Then why? What is the reason they reduce the size of the key? So that controversy exists. Because the design criteria was classified in that way. So subsequent events and public analysis show in fact the design was appropriate only, and they use this DES, and especially it was used in financial applications. Still it is standardized for some legacy or application use, but The 3 DES or triple DES is still strong because it uses 112 bit key. So later on we see what is a triple DES. The base behind this triple DES is this DES only, data encryption standard only. 3 times you are performing the encryption decryption operation there. So generally if you are having more substitution, then it becomes somewhat complex. Permutation somewhat complex. Substitution followed by permutation, more complex it is given. Likewise, DES itself it is a complex algorithm only. 3 times if you are performing DES, so maybe the security is tripled. Likewise, the inventors of triple DES might have an intuition and they decided to come out with that algorithm. Later on we see that. This is the overview of the DES encryption process. By looking into the pictorial representation, this is actually the gist of the DES encryption algorithm. If we expand each and every block, all the blocks are somewhat complex, but at least we must have the basic understanding. So this basic flow diagram or block schematic is good enough to discuss now. So we already know that the input to this data encryption standard algorithm is a 64-bit plain text. So here we are having the 64-bit plain text is given as input to the encryption algorithm. Then we know that we are using a 56-bit key, but actually we are not using a 56-bit key. We are having a 64-bit key. That key is transformed to 56, then it forms as a sub key, that is 48-bit, that is only used in the algorithm. But it is given that it uses 56-bit key, but actually it is a 64-bit key that is transformed, or it's gone through some permitted choice. There some 8 bits are removed, then it is given to the left circular shift. So only the 56-bit key we are using here. But as such, we are not using the 56-bit key. We are generating a sub key of size 48-bit. And already we have seen in the Feastel cipher structure 16 rounds are there. The same operation for each and every round only here also we are performing. And here in the basic block schematic we have given us round 1, because if we expand it becomes very large enough or complex enough and it's very difficult to understand, and we can't draw in a page. So that is also one of the reason. So as of now we are just learning that it is a round 1. Then later on we see how it is expanded. So initial permutation for each and every round some 48-bit key is given, and for the key itself we have to do some operation. 64-bit key is given to the permuted choice, and some 8 bits are removed based on some criteria. 8 bits are removed, and those 56 bits are passed to the left circular shift, and this left circular shift is again given to the permuted choice too, and this 56-bit is converted to 48-bit, and that 48-bit is given as input to the round function. So this much complexity they have incorporated in even the key generation process itself. So obviously by looking into this architecture we feel that it is more secure, because too much of confusion and diffusion we are doing, and we are frustrating the cryptanalyst a lot because we are doing more operation. So the cryptanalyst has to do more work if the cryptanalysts want to break the cipher system. So more diffusion and confusions are performed here. Then after the 16 round, we are just performing a 32-bit swap. Then again that 32-bit swap, two swaps are there, left and right, so only it is forming a 64-bit. Then that is given to the inverse initial permutation, and finally we are getting the ciphertext. So in order to do the encryption process, how much complex activities and computations we are doing. See, so that what is our main objective? We have to improve the security of any crypto system. That is our ultimate objective. So in order to improve the security, we are doing these much works. Then first step is initial permutation IP. Here it is the first step of the data computation. Permutation in the sense, you know, some rearrangement happens. And in this DES, many predefined tables are there. For performing the initial permutation also, that permutation table is there. Based on that only we have to change it. And in the transposition cipher also you have seen, based on the key position we are changing or shuffling the position of the plain text element. The same principle only applied here, but here it is that the table size is somewhat big. So here first step of the data computation, it just reorders the input data bits, even bits to the left half and odd bits to the right half. But it is quite regular in structure. It is easily implemented in both hardware as well as software. So data encryption standard, don't think that we can write only programs, not like that. In hardware also we can implement this data encryption standards and all using FPGA. Many more tools are also there. So using that we can implement all those things. So this initial permutation, it is not giving any cryptographic value, just shuffling only. But they have defined that table. So based on that only we have to change it. First position is a 58 bit, so that the plain text first position has to go to 58th position. By looking into the example, we can see how the permutation happens. Next is the DS round structure. Already you know something about the round structure, because in the last presentation we have seen the rounds in the Feastal cipher structure. The same is only used in this data encryption standard also. So here this DS round structure uses two 32-bit left and right halves. We already know that in the Feastal cipher structure the plain text is divided into two halves, left and right. Then some cross-like computations are there, and one side alone we are performing some F function, all those things we are doing. The same thing only here also it is used. So here the Feastal cipher is used in this DES round, and it is given in equation form that the left half equal to the previous right half and the right half equal to previous left half XOR then f of it is called as Mantel function, f of previous right block comma key k, the sub key ki. So this f takes a 32-bit R half and a 48-bit sub key. So it is here you see that here the value is 32-bit but the sub key is 48-bit. So what we have to do? We have to expand this R to make it a 48. Then only we can apply some computation, because equal number of bits must be there to perform some computation. So expands R to 48 bits using the permutation E. Then we are adding to sub key using the XOR operation, so that it has to pass through 8 substitution boxes to get the 32-bit result. Finally, if you want to get the 32-bit result, it has to pass through 8 substitution boxes, and again we are permuting using 32-bit permutation P. So all those S boxes, P boxes are a fixed table. So as such we are taking that table value and we are just looking into and we are using it. That's it. We are not going to define any S boxes or P boxes. In the algorithm itself, using many trial and errors of experiment, they have defined and they have made as a standard all those things. So we are just using it. That's it. So this is the pictorial representation of the DS round structure. Here you can see that the left half I minus 1 and the right half. This only we are dividing the plain text into left and right. So we are having the left half as well as the right half. And the left half here only we are giving to the XOR function, but we are doing some operation with the right half, and finally the cross structure you can see here, the right half is directly given to the left half. In the previous presentation we have seen that Li equal to Ri minus 1, that is previous left half. So this blocks are repeated for all the rounds. So if you know one block, the same thing is repeated. By why 16 rounds? There is no significance for that number. Using different trial and errors. Why not 15? Why not 14? Why not 17? But there is no justification for that. We are in the Feastal cipher structure, they have given 16 rounds. So we are also using 16 rounds. No need to add something or remove something. So there is no justification for that, but as such we are using it. Because the inventors of this algorithm, they explored many things, they experimented many things, and finally only they come to the conclusion that 16 is a very good round. Number of rounds 16 is giving better result. That is, it is providing more security. That is the meaning. So here the right half, we know that 64-bit, 32-bit and 32 bit. So this right half is passing to the expansion permutation, because we already know the key size sub key is 48 bit. So with 48 we can use only 48, then only we can perform some operation. If it is 32, it is not possible. So we are expanding that 32 to 48, then only we are XORing this value, but finally we want the result in 32 only. Because left half is 32, the right half, the result must be 32 only. So what we are doing, we are giving that 48 bit to 8 S boxes, and we are reducing the size to 32 bit. Then we are again giving it to the P box, that is transposition or permutation box, just in order to shuffle it or rearrange it. Then we are XORing this value with the mangled right half I minus 1. Then again that result is XORed with the left half I minus 1 in order to get the right half of this particular round. And coming to the key, we already know that key is also a 64 bit. But if we pass that 64 bit to a permuted choice one, some of the 8 bits are removed and the remaining 56 bits are only passed through the circular shifts. So here left shifts. So here we are just dividing that 56 bit into left half 28 and right half 28. And for the 28 we are performing the left shift, and another 28 we are again performing the left shift. Then we have to convert it to 48 so that it is passing to the contraction permutation, that is permuted choice 2. Finally we are getting the round key 1, that sub key 1 is generated. Likewise we have to generate all the 16 keys for all the 16 rounds. Next is the DES round structure for this substitution boxes. In round structure we have given, we have expanded from which one, this one, 48 bit operation we have, then we have did 48 to 32 we did, right? Earlier only we expanded, then afterwards we performed substitution in order to convert 48 to 32. So how we are converting that 40 to 38 means, here earlier we are having the right bit, then we expanded here and it becomes 48 bit. Then the key we know that it is a 48 bit. Then they are XORed and it is passed to the 8 substitution S boxes. All the substitution S boxes are fixed. We can't change the value. And here this 48 bits are divided into 6 bits of 8 blocks. And those 8 are given to the S boxes, and those X or S6 are converted to 4 here. If you pass the 6 bits to the S boxes, finally we are getting the answer 4 only. So if we combine that, we are getting a 32 bits output, then that is passed on to the permutation. Finally we are getting 32 bits. This is about the S boxes. How the S box structure looks, later on we can see. So this is the expansion permutation. So where we applied this expansion permutation means we are getting a 32 bit input, but if you want to XOR this 32 bit with the key, we have to make it to a 48. There only we expanded this. So how we perform this expansion means, R half expanded to same length as 48 bit subkey. We are considering R as 8 nibbles, that is 4 bits each. Here you can see one example, 4 bits. 4 bits, that is 1 nibble. This is 1 nibble. Then how we are performing the expansion means, we are just copying each nibble into the middle of the 6th block. All the 4 nibbles we are copying it in the middle of the 6th block, because we need to convert that 4 to 6. So we are just copying it. Then copies the n bits of the 2 adjacent nibbles, this adjacent nibbles, into 2 n bits of the 6 bit block. For this 6 bit we are just copying these 2 n bits, this 12 and 17. Likewise we are doing for all the digits in order to expand the given value from 32 to 48. Next is the substitution boxes. We are having 8 substitution boxes which map 6 bits to 4 bits. We have seen the pictorial representation. So here each X box is actually a 4 little 4 bit boxes only. That is, here the outer bits 1 and 6, that row bits select one of the row of 4, and inner bits 2 and 5, the column bits are substituted, and the result is 8 lots of 4 bits. So only we are getting 32 bits. 8 fours are 32. 32 bits we are getting it. All 4 we are getting from the output of all the 8 S boxes. So the row selection depends on both the data and key. So this activity only we are calling it as auto keying or auto claving. This is one example for the S box, but we will work out some problem. At that time we can see this example. So this is the pictorial representation of one S box. The input symbol 6 are there and we are having the output as 4. So each of the 8 S boxes are different values are only given, and each S box reduces 6 bits to 4 bits. So the 8 S boxes implement 48 bit to 32 bit contraction substitution. Next is the permutation box. We all know permutation means just shuffling only. So all the values are there, we are just changing the position. So we are applying this P box at the end of each round in order to increase the diffusion, that is avalanche effect. That is a single change in the plain text or a key have to change at least half of the digits may get changed in the cipher text. That is called as avalanche effect. So in order to provide diffusion effect, we are having this permutation box. That is single change in the plain text change many bits in the cipher text. Avalanche effect means at least half of the possible bits it is changing. So this is the pictorial representation of DES round and full. First we are getting the right half, then we are expanding from 32 to 48, then we are XORing this 38 bit with the round key. Finally we are getting the answer, and this answer we are passing into 8 substitution S boxes. Then it is reduced from 48 to 32. Then it is passed on to the permutation. Then again it is XORed with one value. Then that is left of I minus 1, it is XORed. Then we are getting the right of I minus 1. So how we have to interpret the permutations? Always the permutations are given in tables only. The inputs are numbered from 1 to n and the outputs are positioned by the position of input in the table. So only I already told you 58 is the first value, means we have to replace that first value with the 58th, the position. So tables are in rows of 8 numbers per row. So the P box permutation just takes bit 1 and moves it to bit 9. Shows this by having 1 in the 9th position. That the first number on the row 8. Because here we are having 64 bits. So 8 cross 8 matrix only we are having in the permutation. So here bit 1 and moves it to the 9th shows means 1 in the 9th position, that is first number on the row 2. Next is DES key schedule. In the key subkey generation itself we are doing many operations. So how the key is scheduled? It forms subkeys used in each round. That is initial permutation of the key. Permuted choice 1, which selects 56 bits into 28 halves. We know that left and right 28 bits. Then 16 stages consisting of rotating each half separately either 1 or 2 places depending on the key rotation schedule K. We are not just rotating one position, 1 or 2 position based on this key rotation schedule. And we are selecting the 24 bits from each half and permuting them by the permuted choice 2 for use in the round function. So initially from 64 to 56, there we are using one permuted choice 1. Then from 56 to 48 we are using one permuted choice 2. Here we are having many issues in both the hardware as well as software implementation. So this is the pictorial representation of the key schedule. First we are having the 64 bits, then with the parity bits 8, 16, 24, 32, 40, 48 and 56 and 64 are removed. 8 bits are removed from the 64 bit, and finally we are getting, so this type of permutation we are doing, and we are getting 56 bit. Then this 56 bit is divided into left shift as well as right shift. Then it is passed on to the permuted choice. Then again we are removing 9, 18, 22, 25, 35, 38 and 40, 43 and 54 are removed, and we are we got a 48 bit key. That is, it is passed on to the permuted choice 2 and we are getting a 48 bit subkey. This is applicable for all the rounds. So coming to the decryption process, it is the reverse of encryption process only. So whatever we did in the encryption, the same thing we have to do in reverse manner. So we are decrypting must unwind steps of data computation. With Feastal cipher design, we do encryption steps again using subkeys in reverse order. So the same step only we are doing with reverse order. So this initial permutation undoes final FP step of encryption, and first round with SK16 it undoes the 16th encrypt round, and finally the 16th round with SK1 undoes the first encrypt round. Then finally we are having the final permutation. This undoes the initial encryption, initial permutation. So we are just recovering the original value. That is, after the result of decryption is we are extracting the plain text from the ciphertext. That's all. So here decryption, how we are doing is the left half I, then right half the Mangler function is applied with the round key. Then from the right we are having this similar to that of the encryption process only, but the reverse way we are applying. That's the only difference. So in this presentation, we discuss about the history and introduction to DES, then the data encryption. There we have discussed all these steps like initial permutation, round structure, expansion permutation, then substitution boxes, permutation bars, then the DES key schedule. Then we discuss about the data decryption also. It is just the reverse of the encryption process. In the next presentation, we will be discussing about one example of this DES algorithm. Thank you.